In this video, we're going to try to tackle the second question, the thermochemistry one where they've got the calorimeter. So it says a technician performed an experiment to determine the molar enthalpy of combustion of propane in a soldering torch, as represented in the diagram below. So the diagram has a thermometer, aluminum cover, water, an aluminum calorimeter, and a propane soldering torch. The first question asks, what information does the technician need to be able to calculate the experimental molar enthalpy of combustion of propane? What assumptions is the technician making in this experiment? And then how can the technician improve this experiment? Should the theoretical molar enthalpy be higher or lower than the experimental? And what is the theoretical molar enthalpy of combustion of propane? So we're going to try to tackle all of these. They're all independent of any experimental evidence, but they're describing the experimental situation. And so to calculate the molar enthalpy, you're going to need the number of moles of propane. The number of moles of propane is going to be equal to the mass divided by the molar mass. So to get this mass, what they do is they get an initial mass and a final mass to get the delta change in mass. That will allow them to calculate the number of moles that are used here. So then they'll get mole. Then they're going to need to, in the calorimeter, they're going to need to get Q equals mc delta T. The M in this case is the mass of water. So they're going to need to know the mass of water that's changing. If they want to be more complete, they'd include the mass of the aluminum calorimeter and add those two Q values. So the overall Q equals Q of water and the Q of aluminum. Now, I'm not sure that would make a difference. It depends whether the aluminum's pretty heavy or not. We're going to assume, for argument's sake, that the aluminum is really thin and that it makes no significant difference. But you need to know the mass. You also need to know the change in temperature and the specific heat capacity. So they're going to need Ti and Tf. Understanding that these things are required to calculate the experimental molar enthalpy can show up in things like numeric response questions. Commonly, that's where you would see this. You might run into a question that's like that if it gave a list of steps that you needed to use. I have seen questions where they are talking about calculating what things do you need? And essentially, you need to have the mass of the combustible, the mass of the calorimeter, change in temperature of the calorimeter. And if you've got those things, you've got enough information to be able to calculate it. What assumptions is the technician making in the experiment? We always are assuming that this is an isolated system, that we're not losing energy to the environment, right? That might include things like that the reaction is fast, that we're not losing heat to the environment, and that all the heat is being transferred to the calorimeter. How can the technician improve his experiment? Probably the technician could make sure that this is an optimal distance between these two things. They've capped it already, so they don't need to do that. They might want a stirrer of some sort to make sure that the water is circulating so that the temperature measurements are accurate. Those sorts of things would probably be helpful to improving the experiment. Something like a stirrer, if it wasn't insulated, they could maybe insulate the outside edges. Insulating the bottom wouldn't be good because that's going to reduce the heat transfer, but if you could insulate it or even put it in maybe some kind of box to contain the heat, those things would be helpful. Should the theoretical molar enthalpy be higher or lower than the experimental value? Well, this goes from the assumption. We're assuming all the heat is transferred. It will not be. With this kind of setup, there's going to be a bunch of heat lost to the environment. So I would guess that, or it definitely should be that the theoretical molar enthalpy should be a higher value than the experimental value, because the experimental value is not going to fully take into account the heat lost to the environment. And then what is the theoretical molar enthalpy of combustion of propane? And this question was essentially asked in the last question about photosynthesis, But I want you to recognize there's no actual experimental values for you to be able to use. There are no other reactions with enthalpies to be able to manipulate. In that case, if I've got the balanced chemical equation, I can use the Hess's law with molar enthalpy of formation. So if I do this, so I get the products times the number of moles times the formation enthalpy of the products minus the number of moles times the formation enthalpy of the reactants, I come up with negative 20 or 2043.9 kilojoule per, and that's not per mole, that's kilojoules, because these are moles times kilojoule per mole. So this is the enthalpy of this reaction, and this enthalpy could then be converted into a molar enthalpy by dividing by the coefficient amount for any one of those chemicals. On the diploma, your answers are going to have units given to you. If it's a numeric response, it's going to tell you, are the units in kilojoules or are they in kilojoule per mole? So there's a dead giveaway on all questions. Pay attention to the units for every thermochemistry question.